So it's a pleasure to invite you again to this seminar today by Gautam Mandal, and he will be talking to us about entanglement entropy in internal space. Okay, over to you, Gautam.
Thank you, Ayan, for inviting me, and hope you get well soon. So let me start my talk. So this is some work in which I am hoping to say a little bit about the work that we had done a couple of years ago, and something that was supposed to come out this week, but maybe it will go over to next week. So let me start. Oh, how does it work? Ah, yes, that's right. All right. So let me first talk about some formalism aspect of this target space entanglement entropy, or more generally what I call fiber entropy. So the first motivation will be purely from the formalism point of view, from the point of view of quantum information theory. And you can see three pictures here, and I consider here the simple example of a 3-qubit system whose wave functions. So can my cursor be seen?
Yes, I can see the cursor. Yeah.
Okay, good.
Yes.
Yeah. So the most general wave function of this system is this one, and in which the states can be 0 or 1. The individual qubit states can be 0 or 1. And so the base space entanglement entropy is something which I depict by this picture in 1, in which what I do is to leave out the third qubit. So I only consider operators of interest which involve only the first and second qubits. On the other hand, I could consider the second figure, which is the target space entanglement entropy, in which I leave out all operators involving the state 1, so that's the excited state, for all qubits. And the figure 3 is like a mixture of both, in which the operators that I'm interested in are a varying number of operators for various qubits. Okay, so for instance, here I leave out, in this example, I leave out all operators of the third qubit, and take all operators of the second qubit, and only the operators involving the ground state of the first qubit. So I'll describe all of these things, how to compute the entanglement entropy in each of these three situations. The first one everybody is familiar with, but I'll still. So I just wanted to say that although it seems to be such a natural thing to go for, but the study of these the target space entanglement entropy is rather recent, and the fiber entropy in all its generality are not even discussed so much.
So I'm a little confused doing one thing.
Yeah.
So here in the psi is the state. So you are talking about entanglement entropy. Then why are you talking about operators? I'm sorry, I'm a bit confused. What's the point?
So instead of okay, good. So there are two alternative ways of thinking about entanglement entropy. One is so in one, let me talk in terms of Hilbert spaces also, states.
Okay.
So in one, I take the sort of what I do is a partial trace over all states of the third qubit. Okay. starting from, so it will be apparent, the relation between operators and the states, the way you want to think of it, that will all be apparent.
Okay.
Yeah. So basically, in this case, by operators, I mean that your relevant part of the Hilbert space is something like the Hilbert space 1 tensor product with Hilbert space 2. Okay, and you want to leave out, the Hilbert space 3. Okay, and the operators that tracing out the third qubit is equivalent to saying that the density matrix that you get in that fashion is the one that reproduces all operators which are operators in H1 cross H2. So that's the one. H1 cross H2, with all its two states. So
Right.
all 4 states. So you can consider operators which take states of this and to retain them in this Hilbert space. So those are operators. That's an operator way of saying it. But let me go to some examples so that it's hopefully clear. I have no idea why it's not moving. Okay. Okay, good. Okay, so let me discuss this conventional entanglement entropy. This is something that everybody is familiar with. So this is what I was saying, Sachin, that I think of the Hilbert space, the full Hilbert space, as the block of H1 cross H2 and cross H3, which I want to leave out. So H1 cross H2, this part I call HA. Okay, and this is the HB. So this is a tensor product of HA cross HB. So in case of this conventional entanglement entropy, which I will also call base-space entanglement entropy, there the it's a simple tensor product, HA cross HB. And then I consider the density reduced density matrix, which I start from the pure state density matrix, which is psi, and then I take a partial trace over HB. And what I get is an operator, which is called the reduced density matrix, because it has this property that, if I consider an operator, a general operator, which is an operator in HA, that is to say, it takes states in HA, H1, H2, and converts it into some state in HA. Okay, so it's an operator from HA to HA. So the most general such operator is this kind of a thing, in which I take the ij ket and I prime j prime bra, where the ij I prime j prime can vary over 0 and 1. So these, so this construction 1 satisfies the property 2, namely that if I take operators which are localized in HA, their tensor product with respect to rho A is the same as its expectation value in the full global state psi. Okay, in which of course I have to do a little bit thing, which is that in order to define this O, operator O, as an operator in the full Hilbert space, I have to tensor it with the identity of the Hilbert space of 3 on HB. So this definition, the equation 1 and this definition, equation 2, are equivalent. So equation 2 is in terms of operator algebra, and equation 1 is in terms of Hilbert spaces.
I see.
Is that clear now, Sachin?
Yeah, just to make sure I understand fully. So I could have taken an operator which could have acted on all the 3 qubits, right? And then I could have also then in 2 I need not have theta times cross identity, right? It could have been a theta which would have acted non-trivial in all the 3 qubits.
Then this will not be satisfied.
Sorry.
Yeah, if the operator is an operator, this operator O is an operator in the whole Hilbert space.
Yeah.
Then there is no left-hand side of equation 2 which will satisfy this.
But can't I just define a partial trace? You are saying if I define a partial trace, it will not be a proper thing to define.
No. The set of all operators here. This statement is about a set of all operators in the Hilbert space. So only if the this operator is a restricted set of operators, which basically it says that my detectors correspond to the first and second qubit, and the things that I can observe refer to the first and second qubit. In that case, there is a simple, okay, so I should say here that this trace is also over HA, okay, that there is a simpler description of the whole system in terms of an operator, okay, which is rho A, such that the trace of this O, which is the restricted family of operators, because it acts only on HA.
Right.
So a smaller trace can do the job, can express this full expectation value. Okay, this trace on the left hand side, I should say, is trace over HA.
Okay.
So it's a it's a smaller matrix than, so rho A is a much smaller matrix than compared to the original thing that you could possibly have. Okay, all right. So
sorry, Gautam, the small, just in the boxed equation that you have, so this actually is basically a basis of all these operators that you're talking about, right? It's a complete basis.
Indeed, absolutely.
So, right.
Okay, so for example, if psi is this very simple factorized state, which is 0, 1, 1, okay, then you can do this exercise quite clearly. You take 0, 1, 1 kit, 0, 1, 1 bra, and then take the partial trace. So that is to say, take an expectation value with respect to the third qubit and vary the state over 0 and 1. That's the, so you will get this one, 0, 1, 0, 1. So this rho A is a pure state density matrix. So of course, it's the expectation value. It's entanglement entropy, which is defined by minus trace rho A log rho A. That will be 0, because this rho A, in principle is a 4 by 4 matrix, but here it's only one element of that comes in this way. So in the 4 by 4 matrix, there is only one diagonal element, which is 1, and everybody else is 0. So you can just do this. Okay, that's one way of thinking about it, but you can explicitly compute the entanglement entropy, and that will give you 0. So there's a trivial exercise. It's 0 because it's a factorized state. And in fact, even if you have a non-factorization in the H1, H2 part of it, then also the entanglement entropy remains 0. So basically, you have to have some non-trivial, what they call is like some Cooper, EPR pair, forming between 2 and 3, or 1 and 3, or 1 and 2 and 3, in such a way that the state is not factorized between HA and HB. Then you will have some non-trivial. So in this example, in which it is some state of the first qubit, doesn't matter which one, times some psi 2, 3, which is the linear combination of this sort, then the entanglement entropy measures, how much the mixing is and how much non-factorized it is, and it's log 2 in this example, in which I have taken equal, amplitude for 0, 1 and 1, 0. That gives you the maximal entropy in this case, which is log 2. Okay, so this is all well-known stuff. And now let me go to the target space entanglement. So the system is the same. It is a 3-qubit system. So now let's do a little more slowly. So now every Hilbert space of the ith qubit. So the Hilbert space for the ith qubit is a direct sum of now A, okay, in this case, will represent the ground state of the qubit, the state 0. For each of these, I'm losing my cursor, huh? For each of these qubits, qubit number I, okay, so A will, is there some way of
no, I think I can see the cursor there. No problem.
okay, all right, yeah, no, now I got it back. Oh, if I'm, Jesus Christ. Oh, maybe there is some thing on the, just one sec, sorry. Is there some, yeah, okay, I think now I got it. Okay, good. So this is A and this is B, okay? So A would be just the state 0 and B for each of the qubits would be the state 1, okay? In this case, each of the Hilbert spaces is a direct sum, right, of A and B, not a direct product, right? Because any state of the qubit number 1 is a linear combination of A and B. Okay, remember A is the 0 state and B is the 1 state. So it's a linear sum. Okay, it's not a tensor product because it's a single qubit. Now for each of these, okay, so here I have defined what HIA and HIB are. They are just this. Okay, here span means just the linear ray corresponding to 0 and B is 1. Okay, now the full Hilbert space, which is the tensor product of all the all these qubits, will have this structure. Okay, so HA plus HB tensor product now. So there's a tensor product here by definition. Okay, so that's HA plus HB and then tensor product HA plus HB. Of course, there H1A plus H1B, H2A plus H2, etc. Okay. Now, if you work out the, if you do this entire product thing, so there are 1, 2, 1, 2, 1, 2. There will be 8 terms, okay, which will be all separated by a direct sum.
I'm sorry, what is AB? I'm sorry, I missed. What is AB?
AB, so A, so HIA is the 0 state for the qubit 1. So
AB, the 0 and 1 state. Okay.
AB and 0 are 1.
Okay.
So now you see what I'm doing is the following. I'm splitting in the space of the states, not in the space of qubits. So for each qubit, I'm splitting between 0 and 1. Okay. So my state of interest now is the 0 state for all of these guys. And the states which I don't care about are the 1 states for all the qubits. Right? So then this product of H1, H2, H3, each of these H's have 2 terms. So therefore I'll have 8 terms all told. Okay, where I'm defining the sector. So H1A times H1, H2A times H3A is what I would call HAA. Similarly, HAAB, HABA, etc., etc. So for instance, AAB is what it is. I take this factor from here, this factor from here, and the B from here. Okay. So HAAB will be H1A, H2A, H3B. Okay. Now, when I want to do a partial trace, what I have to do is to do a sector-wise partial trace. So for instance, for HAB, okay, I have to do a partial trace over H3B. Okay. And then I will have, so in terms of the, again, operator algebra, it would mean that in this sector, I'm interested in operators which take H1A, H2A, and it's an operator in this Hilbert space. So take a state of H1A, H2A, and give me another state of H1A, H2A. Okay, so that's what I do. So I do the same exercise as I did before, but now sector-wise. okay, where I do have a tensor product structure, and it makes sense to talk about a partial trace as I had done before. All right.
Hi, Gautam.
Yeah, hi.
Hi, Lata here.
Hi.
So sorry, I think I joined a bit late. So what is this? So you are not talking about just the product state of 3 qubits. So what is the span here?
No. It is the Hilbert space is the product Hilbert space of the 3 qubits, but it's now the what I'm interested in is different. Okay. So I'm interested in operators which involve only. Okay, so I'm now splitting. So compared to what I had before, in conventional EE, which I would also call base space entanglement entropy, I split the qubits. Okay, 1 and 2 were my qubits of interest, and I left out qubit 3. Now I'm interested in the following. I'm interested in the 0 state of each qubit. So I want to leave out, okay, the state 1 for each one of them.
Okay.
And I'm explaining how to do that. Okay, so I can define this concept, okay, in each of these sectors. For example, in HAAAB, I do a partial trace over the only B that appears in these factors. Okay, so there's only one
also
in the factors. Yeah.
So is it right to understand that you have you allow all the 2 to the power 3 here?
Yes.
States, possible states, and you want to trace out whenever the qubits are in the state
whenever B appears and however many B appears, I want to trace out over all of them, do a partial trace. Okay, so this exercise is actually very easy. And what you do then is to define total reduced density matrix, which is a direct sum of the sector-wise reduced density matrices, and consequently, the total entanglement entropy, okay, in this case, for this region, 0, 0, 0, okay, that entanglement entropy will be a sum of entanglement entropies of each sector, okay?
Hello, sorry. So what about this HAAA? But
yeah,
there is no
in
B, right?
HAAA, there's nothing to be traced over. Whatever I get, I get.
Okay.
Yeah, so there is no partial tracing at all. In HBBB, it will be just a number. I have to trace over all of them. Okay,
yes.
So that will be just a number thing. So indeed, the dimensionality of the reduced density matrices will be different depending on which sector you're talking about.
Okay, thank you.
So you can look at the. So I'll do an example very soon. So the partial trace the entanglement entropy in each sector, if I call this S of S, where S is a sector number going from 1 to 8, and the specific labels are A, B, etc. Then the sum is the target space entanglement. Okay, so this is something that okay, I don't know how to get rid of this black thing that is obstructing me. Anyway, never mind. So there the references I cannot see, but I presume you guys can see it. Okay.
Yeah,
we can see.
Okay, you can see.
Just one question, Gautam. So why it is called target space entanglement entropy? Why are you giving this nomenclature?
Because of the following. So let's go back to this thing here. Here, what I'm doing is that my subregion is defined in terms of the base space. What is base space? Is horizontal. So there are three qubits here. Okay. So which qubits you want to keep is that choice is like what you do in field theory, right? In field theory, QFT, you split, let's say, 1 plus 1 dimensional field theory. You split the line, okay, into 2 subregions, okay, or however many subregions. Okay, let's say A and B. Okay, that, and then all the spins or all the fermions or all the whatever it is are in this interval A. You want to keep, and all the other guys in interval B you want to leave out. Okay, that is what is the normal thing is. So this is exactly that. So think of this 3 qubits as basically lattice points of a field theory system. Okay, and you want to leave out entirely some lattice points. So that concept is the usual base space entanglement. Is that
So can I also think of this target space as some kind of looking at operators which are like low energy operators? So the one is say some excited state, and you only want to.
yeah, if you wish, if you wish, yeah, if you wish, you can do that. So let me say a little bit of in a field theory language, maybe. So there seems to be pain here. Okay. All right. So the just give me one second.
Maybe the target space is like the momentum space where I'm calculating entanglement entropy between different energy eigenstates of the system rather than, and the base space is like the Poisson space analog.
Yeah, let me say it in a probably more. Okay, so in a path integral, you have this in which each of these phi x's, the integral goes from minus infinity to plus infinity. If this is the, and then there is a range of x's. Okay, so if you split the range of x's, then that is what I'm doing here. Okay, on this. So suppose the entire range of x's you split between x belonging to A and x belonging to B. But the range of the integration always remains minus infinity to plus infinity. Right? This is what you do in a field theory. Okay. In a standard conventional entanglement entropy, you split the space, okay, into 2 parts. Now suppose you don't do that. You do the following. D phi x, the range of x's remain the same, but minus infinity to plus infinity, this you split into 2 parts. Minus infinity to 0 and 0 to infinity. Right? You split this range of integration, which is what is the target space, right? That's a fiber. Okay. So in a field theory, there is a base space, which is x. And at each x, there's a phi. There's a phi x, which is a real number. Right? That's a real number. So if you split this real number between two parts, then that is like splitting the fiber. Right? And you say that I'm interested in only this, and I'm not interested in this. Okay. So that would be called. In fact, in target space entanglement entropy, what you do is to split each fiber the same way. And this last one is something in which you can, the subregion of your integration range can depend on which x you are standing on top of. Okay, so that's the most general fiber bundle entanglement entropy. Is this clear? Does it make things a little clearer?
Yes. Yeah. Okay. Yeah. Now the nomenclature looks clear.
Yeah. So can I add one just maybe a question comment?
Yeah. Sure.
So what I was saying that, if I try to define entanglement entropy in the momentum space rather than in the Poisson space,
yes,
the integration will still be all over the space, but I'll be splitting my Hilbert space in terms of the energy eigenstates or the momentum eigenstates. So I'll take a particular set of momentum eigenstate. How is it entangled with the other? So it would be like the target space kind of thing, right?
No. Momentum space is still here. So instead of the x's, you are doing k. And then let's say you are interested in, a subregion of k space. Okay. So let me say, So the base space entanglement entropy that I talked about here is that you use X space.
Yeah.
Like that. Okay. But
Right.
that, however, the d phi k integral, so the integrals over d phi k still go from -infinity to +infinity.
Right. So what I was just commenting is that in the momentum space, base space and the target space just get switched over. That's what I was just.
No.
It does not. Okay.
No. So
Okay.
whether the base space is labeled in terms of x or k, okay, it's still base space, meaning that all the phi x variables, this entire set of phi x variables, they are labeled differently. They are labeled differently.
Okay.
So it's the labeling of the base space changes. However, each of these fibers, okay, they still go over, the full range. I'm not splitting in the full range. Okay. All right. Good.
Sorry, can I just ask for a small clarification? So basically, in the quantum sense, these phi's are operators, right? So would it be all right to say that, your target space entanglement is essentially partitioning the operator space and finding an entanglement there? Is that
You can
right?
say, indeed, you can say that. So you can say that, it's the actually, this, all three examples here are instances of a more general notion of defining operator subalgebras. And depending on what operator subalgebras I choose, it can look like base space entanglement, target space entanglement, or general fiber bundle entanglement. Yeah, you're right about it.
Yeah, so basically in the target space entanglement, the fact that it is like a split in the operator space of operators.
I mean, in all cases, no. In all cases, this is split in operators. So here the operators are ones that, that are in this block. Here the operators are in this block. Okay. And here the operators are in this block.
Yeah, but what I wanted to say was, in the first case, where, the usual base space entanglement, there would be some operators that would take you from, like, one part of the Hilbert space to the other, right? There will be some mixed operators like that, right? So it's not really a split in the operator space.
Yes, right, indeed. So you are not considering operators which connect this block to the third one.
The third, yeah. So there exist such operators, but we are not considering, in that kind of Hilbert space factorization.
Okay, you are not interested. For example, in the lab, okay, when you have a when you have a large sample, you may be interested in correlation functions of some close operators in a certain subregion.
I see.
Then you can take that subregion to be your subregion of interest, and the remaining guys, okay, you call B, and you are not interested in them.
Okay? I see.
And there's no point in specifying the entire, global wave function, which is of no use to me.
I see.
So that is how this concept actually came first.
Yeah.
Okay, let me go. In fact, I don't know.
Maybe for interest of time, we simply move ahead. And,
okay, all right. So yeah, no, actually, these are all interesting questions, and these parts are interesting. So let me go to the example in this case of a particular wave function and how this sector-wise thing works out. Okay. So let me take so how to do it. So the definition is the following: take any one of the sectors. So I'll take HAAB as my sector. Okay. Then there's a projection operator. Clearly, you can define a projection operator which does the following: if a wave function, if a state is an arbitrary mixture of these or the 8 sectors, then there is a projection operator which will project out the part that belongs to AAB. Okay, so that projection operator I call PAAB, and I call that state psi AAB, which is the projected part of psi. Then I construct the following density matrix, which is a pure state density matrix, psi AAB ket, psi AAB bra. And then I take, in this case, I want to take, so my Hilbert space is HAAB. So I want to trace out all the B's that I see. So here the B is in the third slot. So I take a partial trace with respect to H3B. Okay. So that gives me some, operator in the, so this is the density matrix, which is an operator in HAA. It's an operator that takes HAA and it's a map from HAA to HAA. What do I mean by HAA? By HAA, I mean this precisely. Okay, I take HAAB, okay, and I ignore B. Okay, that's something that I would call HAAB or HAAB slash. Okay, so that's the, so I take the row AAB and compute the entanglement entropy with respect to this density matrix. Okay, and so in case of the general state, A1, A2, the linear combinations being the amplitudes being called A1, A2 up to A8 because there are 8 sectors. And then you can do this exercise here that the row AAB, first of all, in this state, at this stage, it will be this, right? The Kate of this and the brow of that, the same guy. And then I take a partial trace with respect to the third slot. That means that I just take partial trace with respect to the B of the third slot, right? So that's just the state 1 of the third qubit. Okay, so I do that stuff, and then I get 0, 0, 0, 0. This is some, by itself, this is some pure state projection operator. But so you might think that, okay, row AAB, it seems to be like a pure state. So therefore, the density entanglement entropy will be 0. Not quite, because it's not a normalized, projection operator. It is precisely this coefficient that appears here that gives it a non-trivial entanglement entropy. So now you do this minus trace HAAB slash of rho log rho, and what you get is, this is an easy calculation, minus A2 square log A2 square. So let me go a little faster. So now,
sorry, sir. In the previous, this entanglement entropy between what and what?
There's an entanglement entropy. Okay, so in this sector, it is an entanglement entropy between HA and HB. Let me go back.
HA and HB.
So it's an entanglement entropy between the A factors and the B factors.
I see. So I see. I thought you wanted entanglement entropy between AAA and BBB. It's not like that.
No. In each sector, what you do a partial trace over, it depends on the that sector.
I see. So in B, don't I have to sum over also A? Sorry, if I'm just interested in entanglement entropy between AA with, or just AA with B. It's not.
Yeah, 1A. So what you are doing here is the following. It's the entanglement between 1A, 2A with 3B.
Okay.
Right? That's what it is. Okay. So for interest of time, let me just give you the result. It's actually quite the same as what we did for the example sector there. So here for the AAA sector, it will be A1 mod square times a pure state projection operator. For row 2, which is something that we have already done. So the sector 1 is AAB, etc. Anyway, so all this is easy stuff, and what you can see finally is that the sector-wise entanglement entropies are these. So there are 8 expressions. You add the 8 expressions, and you get this stuff: A square log A square. Of course, this example was a little too simple because it was a qubit system with 2 levels. Suppose you have 3 level qubits, then you can have something more non-trivial in which this row 1, row 2, these guys will become actual matrices, not just a projection operator. It will have non-trivial or diagonal and off-diagonal elements in that stuff. So it will be a little. So I don't know what I'm seeing here. Okay, so let me. Yeah, I can't see this. There is a zoom.
Yeah, we can see the laser.
But I can't see. Okay, so anyway, I think what I have written here, I have to guess, is that the each of these row 1, row 2 guys will have a normalization and correctly normalization constant and a correctly normalized density matrix. I think I have called them rho hat, and then the total entanglement entropy will have a structure like this, okay, which is like a classical entanglement entropy, and it will have a non-trivial thing, which will have within each, it will have the quantum part. Okay, let me say that.
Sorry, this total SE is entanglement entropy between what and what? I am confused. Sorry.
Total entanglement entropy is between the A's and the B's. So between this block and this block. The point is that this block and this block, the notion itself is not so easy to define, because at this stage, let us say if you have only one guy, okay, one qubit,
Right.
then the state 0 and the state 1, they don't appear as tensor products, okay, because the state is a simple linear combination of 0 or 1. You don't talk about partial tracing and entanglement between 0 and 1. That doesn't make sense. Okay. So in order to talk about so what is being done here is the following. Let me try to do this. So in HAAB, what you are doing is the following. You are doing entanglement of this with this.
Yeah, HAAB, I understood that it's an entanglement between AA and B.
Yeah.
But when I have summed over everything, it looks like it's an entanglement between everything with everything. So, sorry, I got a little confused with that.
No. It is still an entanglement entropy in which only so maybe I should have written the operators. The operators are such that in each case, they are always taking something, yeah. So let me try to do this.
Well, in each subsector, you are simply tracing out the B sector.
Yeah. So for instance, here in HAAB, the operators
pretty well different.
are like this, which are in the 1, 2. Okay, that's the operators. Here, AA is the trivial one. It is 1, 2, 3, and this is the operator. 1, 2, 3, and so on. So all your operators are only things which involve the ket 0. Okay, whatever number of zeros it is. So your operators always take, okay, let us say,
I see,
the whole thing to itself, or this guy to itself, or this guy to itself, and so on and so forth. They don't touch the states 1 at all. Okay, that's what that operator is. That's
basically some kind of conditional tracing out in some. So it is conditioned by the subsector you are.
It's a condition. So it's a restriction in the target space. Okay, it's a restriction in saying that I'm taking only 0 and not 1. That's it.
I see. What I just got confused with is that you are getting all sums, right? You are getting sum over from 1 to 8, all the sums, and they are just coming uniformly from A1 to A8.
But you see how the things are. It's all A's here.
Yes.
And here it's AAB.
Yes.
But I trace out B to make it AA. and so on. So eventually,
I think what Sachin is confused by essentially is this conditional aspect of the tracing out. So it is not a tracing out like normally you just simply trace out 1 degree of freedom. That's an end of the story. But here it is more of conditional. Depending on which subsector you get, you trace out certain.
So for example, for HBBB, will you get any contribution from HBBB? Will you get
nothing at all? It will be a number. It will be a number.
So, but you are getting sum over all the A1 to A8. That is what I got. I thought you will not get any contribution. Maybe it will stop up to 5 or something. Or
No. It will be a C number. HBBB will also give you something in which, because okay, I'll tell you what HBBB is. HBBB is something which is this. So you first do the projection psi BB. So psi BBB will be A8 times 111. Right.
I see.
Now you have BBB here. So you bracket all the BBB, meaning that you trace over the whole thing, HBBB.
I trace over the whole thing, I see.
So that HBBB will just take care of this guy. It will be just 1.
Okay.
So now you will be just left with A8 mod square. That's it.
Okay.
So it will be only a kind of classical contribution from the sector, no quantum like contribution.
Yeah, that's right.
Looking the substructure.
Yeah. However, that was for the 2-level qubit. But if you have 3-level qubits, qubits or something, then you can have you can have non-trivial operators in each one of these things, not a projection operator. Okay, let me give you some nice example of a possible it will be fun. So let me take a factorized state. Okay, but in each one of these things, from the point of view of the Z spin, from the point of view of the sigma Z operator for each one of them, it is non-trivial because it's not completely aligned or anti-aligned, right? It's a linear combination of 0 and 1. So for in each of these qubits, okay, it's a non-trivial linear combination of 0 and 1, and I take the same guy, okay, for all of them. You could also play with different linear combinations in different, but it's factorized. Okay, as soon as it's that it's factorized, okay, the entanglement entropy, the base space entanglement entropy will be 0, right? So you might say, okay, what's going on? After all, there is something non-trivial about this state, okay, but it just gives you 0. Now comes, now comes the target space entanglement entropy. If you compute the target space entanglement entropy, and it's an easy calculation to do, you will find that this is the target space entanglement entropy as a function of B naught. By the way, you know that B naught is just 1 minus B naught. So B1 is 1 minus B naught. So that's not an independent quantity. So this the target space entanglement entropy in this case is something non-trivial, and it is maximized when this is the most non-trivial linear combination of 0 and 1. Okay, so this is something which probably we have been looking for, So let me give you some work that's in progress, but let me tell you where this could be useful for. Let's say I'm doing a global quench, okay, in a system in which, let's say I change the mass parameter or something, and it's a massive theory, so that it is more or less the ground state, okay, is more or less factorized, okay, because the the amount of entanglement between neighboring lattice sites is small if it's a massive model. In a massive model, because it's more or less completely entangled, the base space entanglement entropy is no good because it will give you basically 0. Okay, but when you do a global quench, okay, you are doing something. You're changing the Hamiltonian from one value of the Hamiltonian. Let's say the I'm changing the magnetic field coupling from some value to some other value. So clearly the alignment will be, let's say, from very strong value to some weaker value. So the alignment will change, okay, in each lattice point. So therefore, there is something here, okay, in massive models, and when you are doing some global quench, which is not, which does not distinguish between one lattice point to another and another lattice point, okay, then this is a potential new tool which can give you some change in entanglement that's happening in the dynamical process. Okay, so I'm saying it a little qualitatively because that will take me another full talk to explain what this is. But I'm saying that even when the lattice sites or the qubits are in a factorized state, but the state in each of these lattice points or the qubits is non-trivial, then there is something which expresses that, some entanglement notion which expresses that non-triviality. Okay, good. So
can I ask something? Maybe you have it in your slides later.
Yeah.
Suppose I consider matrix models, like BFSS or something. Would you use it to describe something like?
Absolutely, it will come. It will come. So we'll talk about C equal to 1 and BFSS and so on and so forth to some extent. BFSS is probably not that much because that was in the earlier work, but I do have slides on that. If I have time, which I doubt, then I will talk about the BFSS as well. Okay, but the C equal to 1.
One small quick clarification. So, the way that you have generalized, I mean, is it somehow very obvious that, let's say, some of the, salient properties of usual base space entanglement entropy, for instance, subadditivity or other inequalities, they kind of go through for this target space as well? Is that obvious, or they have to be derived? Can you make some comments about it, please?
Yeah. Some things work out, but that's a very good point. And I don't know. The answer is I don't know. Some things work out, but what is the total, or even more generally, with some very general operator algebra, what all can be said? I mean, maybe people know this, but I'm not an expert in this abstract, entanglement entropy based on operator algebras and so on. Some things I can see by construction and examples, but general statement would be very, very important to know. Yeah.
Gautam, just one quickly something. I think maybe it will come, but I'm missing the motivation. I think you said it in the global quenches in massive models. But for example, in this plot, if I have the initial state is a product state of the each qubit is in a superposition, but essentially it is a product state. So you get a no change. You have zero entanglement entropy.
The kind of motivation that you are looking for will come in 2 slides.
Okay, because I was thinking this parabola, I am quite sure one can derive analytically for this case where we have a product state. But if there is a global quench, some time dynamics, what physical aspect are we probing actually by target space entanglement entropy?
Yeah, so that I can tell you in slightly more detail. You see, suppose that I do a global quench, and throughout the quench procedure and post quench, it remains a massive model. Okay, so it is almost factorized, right? Because what is the entanglement between one lattice point and the neighboring lattice point is just given by the Green's function. Okay, so if it's a massive model, then the Green's function is short-ranged. So it's so therefore you would expect that the entanglement entropy for such a state may not be too eliminating. However, the quench that you are doing is in some parameter, okay, which is not affecting the mass so much, but it is changing. Let's say it's some magnetic field coupling or something like that. So it is, or yeah, I mean, I can tell you later privately, but it is exactly like this kind of stuff, that at each lattice point, okay, it is becoming from 0 to a non-trivial linear combination of 0 and 1. Okay,
Okay.
So more generally, you can have phases in which,
Yeah.
it is there's a double well potential, okay, and it becomes a non-trivial linear combination between one well and the other well, okay, and if that all is happening without spreading out in the lattice too much of the correlation of the entanglement. But it can still do non-trivial things in each lattice point. That's the. But
yeah,
I guess.
I mean, this reminds me of people
Yeah,
do these
shall
variational preparation of states, like often, and there they want a cost function. I think this is a very costly cost function, but this could also serve as a cost function, whether you have reached a ground state or not in the variational state preparation.
Not the kind of ground state that probably you have in mind. I'm talking about a massive model, very, very massive model, in which
Okay.
the ground state wave function itself will be almost factorized.
Okay.
Right. So,
sorry, for interest of time, we can move and take questions later and more. Yeah.
Let me go. All these are interesting questions. So the general thing is something that I call the fiber entanglement entropy, and so this is the homework that I gave you, is to work this one out. Take this the same state, which is the general linear combination of the 8 possible states here, and what is the entanglement entropy of this one? Okay. So the answer I gave you here, which I can't see, but there is some answer, and there must be a way of doing this. How can
I? We can see the laser point here.
Got it.
Actually,
now I have banished it. Okay, here it is. So it is this with only the coefficients 2 and 6. Okay, so it's this guy and the 6th fellow here. So there are 2 sectors only, and you can work out the corresponding density matrices and so on and so forth. So it's something that is doable, and it's concrete. Okay, that's all I wanted to say, but I'm not deriving it. Okay, good. So now, okay. So more reasons to look at the target space entanglement entropy. So rather than this qubit stuff, so first of all, I should say that is something that is natural for quantum mechanics. Okay. So in quantum mechanics, what is the thing? Let's say we have n particles on a line described by some wave function psi x1, x2, xn. Okay. Then it's the same thing as what we did for qubits. Is that you can do 2 things. You can leave out some of the particles, or you can keep all these particles, and you can ask that, what is the entanglement entropy of an interval A of the real line? Okay, let us say this is an interval A of the real line. And you can ask yourself the question that in a quantum mechanical system, what is the entanglement entropy of an interval A? Okay, with respect to its complement. Okay, and when I do this, so I have to consider each particle, okay, with some amplitude to be in A, and to be in A complement, and for particle 2 also some amplitude, etc., and it will automatically become a sector wise. Remember here that in this situation, okay, there is no base space. Okay, because the quantum mechanics is like a 0 plus 1 dimensional field theory, so there is no base space here. Okay, but there is a target space. That's where the particle lives. So where the particle lives is a target space, and it makes sense to talk about the entanglement entropy of, let's say, half line with respect to the other half. Okay, and that actually becomes a target space entanglement entropy by definition. And again, as I said, target space entanglement entropy can be a new tool to classify quantum mechanical wave functions in terms of entanglement content. And that is the only tool for entanglement anyway, what you have.
Sorry, a quick question here. So how
Yeah.
do you define the tracing out operations here? There is no tracing. I mean,
The
this
same.
is a level, but it is, you don't have a fact.
The same as in here. The same as in here, you do, you know, you can think of these guys as like qubits. So instead of n particles, you could have n qubits, and you know, there are a certain number of states in this one. You know, the x gets when x belongs to A, and x gets when
I see. I understand.
and this, you know, all that stuff.
I
Okay,
see.
all right, good. So now let me go to holographic motivation. You know, target space entanglement entropy in the boundary theory. So you might ask the question, what is it in the bulk? And you can ask the other way around also. What other way around means, I'll have to tell you. But oh wait, Oyon, what is this? I have already crossed. So give me some deadline. I mean,
yeah, I mean, you can like 20 minutes more, or should be that fine, or
yeah. No, 20 minutes.
Some things about Gautam never change.
Thank you so much.
Okay, so we will hold off questions so that you can finish, and then
I just wanted to make some basic points, and you know, the rest are in the paper. So anyway, so the one example is a C = 1 you know, matrix model, which becomes a theory of particles. Okay, so again, therefore, C = 1 is pretty much like this. Okay. Now you can ask the question, okay, I consider target space entanglement entropy of C = 1. What is it in the two-dimensional string theory, which is supposed to be some kind of a holographic dual, the oldest known holography. And here, lo and behold, it will become a base space entanglement entropy in the bulk. Okay, and so I have just you know, said it here that, you know, the matrix can be diagonalized. C = 1 matrix model is a model of time-dependent matrices, so it can be diagonalized, and each of the eigenvalues behaves like a Fermion. And you can consider. I'll come to this, of course, in greater detail. So so there's one example in which we can say a lot of stuff. Okay, so this is the thing that you know, basically, I can have a second quantized formulation of n particles, okay, in which case some restriction on the range of the x's, okay, become in this language a restriction on the range of the x's, but now x has become a base space. Okay, here there is no base space, there is only target space, but this target space here switches to being a base space. Okay, but I'll explain this in more detail. Is this clear to people that, you know, there is a second quantized version of any many particle problem, okay, in which this is many particle quantum mechanics. So therefore, you know, the particles can move, you know, in a target space. There's only one space, which is target space, but in terms of the second quantized formulation, that x comes into the argument of the field. Okay, here x is the dependent variable. Okay, it's a function of t, and that x now goes into the argument of my variable, so it becomes an independent variable, so or base space. Okay, so that's the main point. So if you miss everything else that I say about C = 1, just the conclusion would be good enough. Okay, so this is what I said, the target space entanglement entropy becomes the base space entanglement entropy in the bulk. So it's essentially the second quantized formulation goes over to the density of eigenvalues, and that goes over to the tachyon of the two-dimensional string theory. Okay, and it is the base space entanglement entropy of the tachyonic field in the field theory that is the target space entanglement entropy. Okay, all right. So that is one example. The other way around here is the following. Suppose you have some fibered bulk, namely some ADS cross S or ADS cross R, that kind of a thing, in which, you know, from the point of view of something like a graviton field or a metric field and so on, okay, the x's and the, you know, the angles in this case, they are all arguments of the metric field, right? Consider a theory of, supergravity theory in ADS cross S, right? As in Maldaceno's duality. In that, of course, the metric will be a function of all the ADS cross S variables, right? In particular, it will be a function of the S variables also. So it will be something like a base space entanglement entropy in the supergravity limit. But in the boundary theory, okay, you don't see thetas as appearing as, in the argument of the boundary fields. In the arguments of the boundary fields depend only on X, okay, and T, of course. So this is all being done. This entanglement entropy, so we are always talking about fixed T, so you can forget about T, okay. So in the boundary theory, only X corresponds to the base space. What does the local information in a small range of thetas correspond to in the boundary theory? Okay, so this is also related to the issue of bulk reconstruction on this S. Okay, a small placket on this sphere. Okay, in excuse me, which I can identify by, you know, allowing thetas to be excuse me, allowing thetas to move around in some very, very small subregion of the sphere S. Okay, how do I construct that in the in the boundary theory, which does not have thetas as a base pair? Is that some kind of a target space entanglement here, etc.? So that's the question mark that I have, and in a restricted set of examples, I will show that the answer is indeed yes. Okay, let's go. DP branes, in particular D0 branes. So D0 branes, okay, are given by 9 matrices like this, xi of t. Once again, when you talk about a fixed time, then there is no base space for the D0 brane description here, which is BFSS matrix model. And here you can consider target space entanglement entropy on the left hand side, okay, because that's the only entanglement entropy that there is. So you can consider some 4-dimension 1 subregion of R9, and what does it? What is this in the bulk? Okay, that's one question that you can ask. You can ask also the other way around, that the entanglement entropy of a subregion of the fiber in the bulk, okay, what does it correspond to in the boundary theory? Okay, so just hold on for 2 more minutes and I'll give you the answer to this question as well. Okay, all right, so this is the right, so that's the plan. This is supposed to have come at 15 minutes. So motivation is done, a lot of them. Summary C equal to 1, I will go over very briefly, and the holographic questions that I asked that I will go over in very quickly. C equal to 1. C equal to 1. So this is like a 1-slide crash course on C equal to 1. Is the time-dependent matrix quantum mechanics here. So this is Mij of t. And these are the eigenvalues. The eigenvalues behave like fermions in an inverted harmonic oscillator potential. And one of the favorite things which is used by Sheehan and Ashok and so on is the model in which the classical physics is only on the right hand side of this wall. Okay. And there is only some quantum mechanical tunneling through this. And you could do, a two-sided thing also, but we will actually look at only the one-sided. In this case, there is, okay, so first of all, here itself, I use this fact that the non-interacting non-relativistic fermions can be written in terms of a second quantized formulation, which is a non-relativistic second quantized fermion theory. Okay, and D equal to 2 string theory, okay, everybody knows it, or otherwise, there is a recording of this talk, or there are umpteen papers of mine and many other people. It's written here, and so this is the space-time two-dimensional action for the string theory, and there is only one propagating mode, that's a tachyon, and that tachyon gets identified with the psi dagger psi. So psi dagger psi at lambda t becomes essentially the tachyon of in which the lambda has to be identified with x in this particular manner. Okay, so this is not so. Okay, let me tell you how this target space entanglement entropy and base space entanglement entropy identification comes about. It is a little non-trivial, but it's straightforward. But principle is very simple. Principle is the following: when you talk about the quantum field theory, or the second quantized version of it, okay, you don't talk about Hilbert space number 1, 2, 3, 4, etc., etc. You talk about Fock spaces. So there's a 0 particle state, 1 particle state, 2 particle state, etc., etc. All particle states. Okay, the fermions. And now, however, the 1 particle state has the same, thing as before, split as before, right? Which is HA plus HB. And H2, which is a 2 particle Hilbert space, has HA plus HB times antisymmetric product of HA plus HB, and so on. Now, the second quantized formulation of a non-relativistic quantum many particle quantum mechanics, what is that? That is basically saying, look at the n particle component of the Fock space. When you look at the n particle component of the Fock space, it has the same structure as in case of the many particle quantum mechanics. So it will have the same structure as the sectors and blah, blah, etc., etc. And when you do the normal base space entanglement entropy, it becomes, this is a little non-trivial, okay, but straightforward again. So you do it according to your known knowledge of base space entanglement entropy, and here you do according to the sector sum, and they actually become equal. Okay, this is something that you can show. Okay, so the as a result, this is some calculation which was first done by in a beautiful paper by Schmidt in 1995, and then it was defined by Hartnell and Mazenk in 2015, and there's some stuff that I'm doing with my students here. And so the entanglement entropy is given by some formula. So let me just say what x2 minus x1 divided by some coupling constant looking object. Okay, so let me cut out the whole story. Here it is. The lesson from the C equal to C. So what this equivalence does the following. It tells you that, okay, D equal to 2 string theory, when you think of this as the low energy field theory, then there's a Cardy-Calabrese formula for the entanglement entropy of an interval, which is this, where epsilon is an ultraviolet cutoff. On the other hand, what you get from the target space entanglement entropy point of view is a coupling constant here, not a UV cutoff. Okay, you get this. So this is the main import of this correspondence, is that the target space point of view tells you that the ultraviolet cutoff of the string theory is to be replaced by, it's actually a thing, okay? It's ultraviolet cutoff should be replaced by N. So N appears as the ultraviolet cutoff. And here's a very simple, the picture of this, which is the reason why this difference comes is that in a Dirac sea, okay, if you do this exercise of, Cardi and Calabrese, in a Dirac sea, massless, you will indeed have an ultraviolet divergence, but here Dirac sea will be replaced by a Fermi sea. Okay, for a fixed n, however large, it will have a finite bottom. Okay, so that actually therefore says that n behaves effectively like a UV cutoff. This is a very important point, and it would seem to be relevant for this string worldsheet way of doing entanglement entropy, the stuff that Atish and Witten and other people are doing. This is like a prototype of that calculation. Okay, so once again, so this target space entanglement entropy therefore says something like the space, actually the kind of space that you get here is actually granular. Okay, there's a finite grain size so the UV cutoff being replaced by some n. So for finite n, there is a certain grain size of space. Okay. Now let me just can I have 5 more minutes, Oyon?
Yes.
Okay. So let me say how this in more non-trivial examples of the ADS cross S or ADS cross R, Rn, the holographic entanglement entropy versus target space entanglement entropy, how do these maps go back and forth? Let's remind you of the Ryuta-Kanagi result. The Ryuta-Kanagi result is the following: that let us say you have pure ADS space and you want to compute the, and this is your boundary theory at R equal to RUV. And let us say you consider some region A of the boundary theory, okay? Then the entanglement entropy in the boundary theory of this region A with respect to the complement is given by the area of the minimal surface, this one, okay? R0 is the turning point for this surface. And if you, so the Ryuta-Kanagi prescription is that you divide the area by 4 times Newton constant, you get holographic entanglement entropy, and there are myriads of examples in which the entanglement entropy could be computed also in the boundary theory, and indeed this is match. Okay, so suppose instead of ADS, we have ADS cross S. There is some fiber direction, okay, which normally, n equal to 4 super NMS series does have. I mean, it's an ADS 5 cross S5. And you consider a subregion not of ADS, okay, boundary directions of ADS, but a subregion of S. Then how does the holographic correspondence of entanglement entropy go? Okay, so in this paper, in the ongoing paper, so I don't know whether I have given the references appear here it is. Yeah, so this is the paper that we are almost finished with Shumit, Anurag, Kanhu, Kishore Nanda, and Mohammad Radwan, and Sandeep. Okay, so the idea is the following. Let us take at least the case in which the ADS cross, Rn or Sn, whatever that factor, I'll call Mn in general. So ADS M cross Mn, and this cross need not be, a direct product. It can be some warp product. So the, the size of Mn can depend on where you are in ADSM. Okay, so so let us say there is a situation in which an IR region, some infrared region appears, which looks like ADSM cross Mn, and however, you can find that this is an IR region of a general, RT surface of a theory in which the UV is just an ADS. Okay. And what you do is take this, subregion A of the base space here in such a way that when you come to this side, then this A is entirely a subregion of M. Okay, so you see what I mean? That, okay, so there'll be examples in which it will be immediately clear. You can do this. Okay, so you are interested in the following. You are interested in a subregion of this fiber Mn. But you can extend this theory in the UV to such a situation that this subregion just becomes a subregion, of course, of the whole space, because there is nothing else that's there. But you have to choose the subregion A in such a way that it does not extend in the ADS M part, but it extends entirely in this one. Rather, I should say, excuse me, it wraps all of the ADS-M part. It's not localized in ADS-M, but it's localized in MM. Okay, so there are examples that we have worked out here. One is the ADS4 going to ADS2 cross R, which is something that you will get near extremal Reisner-Nordstrom black holes in ADS4 or ADS5 and so on, more generally. And you can work this thing out. And let me tell you what happens in the field theory. Okay, so this is something that you can do. You can compute the shapes of the surfaces and so on. This is the Reisner-Nordstrom black hole metric. And so what you expect more generally, in some cases it is known that there is some n+1 dimensional CFT that flows in the IR to some CFT1 or near CFT1, as in the SYT case, and times an MN. Okay, so in the CFT also some fiber appears. Okay, from the whole from this whole thing here. So this such a flow and the corresponding statement about the flow of the entanglement entropy. This is something that is important. We are doing it now, but we don't have concrete results. But we do have some prediction for the field theory, which is the following: that in the infrared limit, there is an area or there is an entanglement entropy that you can compute. That is this term, okay, which is exactly what you expect from a field theory in which the the transverse space does not introduce a new gap. So transverse space, the lowest excitations in the transverse space also are gapless, and so the excuse me. The more important point is the following: that there is a well-defined IR limit. The full area, in fact, of this entire thing can be identified as a well-defined IR area plus some UV divergence, which you can subtract out by some subtraction procedure. Okay, so forget about the gapless remark. The more important remark is that there is a well-defined IR limit, and in fact, you can say a little bit like you can take a sliding cutoff. Instead of a cutoff here, you can take cutoff here. And when you move the cutoff a little bit away from the IR limit, you can identify in field theory terms what the correction is. So the correction is 1 + 2 delta lambda divided by lambda IR. It's exactly like an RG flow equation. So the challenge for the field theory is to reproduce this calculation. Okay, there's a similar thing that you can do to ADS n + 2 to RM. So there's a beautiful work due to Token and Krause, in which ADS5 goes to ADS3 cross R2 in the presence of some magnetic field. There's a brane solution that's there. In the presence of the brane solution, it becomes like BTZ cross R2. In this case, unfortunately, the IR entanglement entropy does not decouple from the UV cutoff appears multiplicatively here. So in fact, the physics remains dependent on the short distance physics, and so this is something. So it's not to say it's not. Therefore, you cannot say that there is a well-defined, isolated IR physics which in which we can forget about what this object is. And so this is some situation which is different from the ADS2 process, etc. Okay, so this is the Docker form. The excitations in the internal directions, they're gapped. The physics is the same as the Landau levels because there's a magnetic field that is involved here. And so you might say that instead of an RG flow, why go to this RG flow geometries? Because there's a no-go theorem by Graham and Karch, which is that if you want an RT surface which extends into the radial direction, then the only subregion, it seems, which is allowed is a hemisphere, is a perfect hemisphere going to the equator. Okay, so the and so that makes them rather dumb because there is only one possible subregion that is allowed. However, there are two ways to avoid this no-go theorem. One is already something that we discussed, the work product, ADS process, as in case of the flow geometries, and the other thing is that so their theorem is true for the infinite ultraviolet cutoff, and so take a finite cutoff, and then you can get non-trivial results. So here it is. You can do this exercise for DP brane geometry, as in the case of this ADS3 onwards. A similar thing happens here. Is that so DP brane geometry? So if it is a D0 brane geometry, then it's like an ADS2 cross S8, and so you get a cutoff dependence. Basically, you get a cutoff dependence in the IR. So the IR physics for the entanglement entropy does not decouple from the UV physics. Okay, and so this is from an old paper of Itzhaki, Maldacena, Sonnenschein, and Yankelovich, which is the ADS CFT for D0, D1, D2 such branes, and the UV physics is something that's in here, and it seems that the perturbative quantum super quantum mechanics description somehow does not quite decouple from this type 2A supergravity range. Okay, so here we are at conclusion. So we discussed fiber entropy a lot. Factorized states can be non-trivial in terms of target space entanglement entropy. There's natural application to quantum mechanics because only entanglement entropy is the target space entanglement entropy. So for C equal to 1, I have shown this, that N becomes a cutoff. And application to holography, I have discussed with Graham and Karch theorem how to avoid this in terms of RG flow geometries. And in case of at least ADS2 cross, higher dimensional thing, there is an easy understanding in terms of the boundary target space entanglement entropy in the boundary. So the fiber in the bulk space becomes like the fiber in the tangent space, and the entanglement entropies should also work out. And well, thank you very much.
Thanks, Gautam, for this very nice talk. Maybe I can open with some. So the first question, this thing that you're having a problem in defining this this UV, there is this UV dependence in this of the entanglement entropy. Does this somehow reflect, of course, the thickness of the operator that we're trying to define, and or is it what is it? In the usual entanglement entropy case, we know what where the thickness comes from.
Yeah, you see, in the entanglement entropy calculation, there is no guarantee that there will be some kind of Wilsonian decoupling, because the Ryu-Takanagi surface starts out at UV, okay, and it goes into the IR. So in case of ADS2, it's a lucky break that it sort of decouples in the sense that the area of the area of this entanglement area of that part of the RT surface which remains in the UV region, it just is an additive contribution, and you can just subtract it out. It's just some UV divergence which you can get rid of by countertime. And it's not clear, why that should be the case all the time. And it is indeed true. But I must say that, I would like to have a field theory answer to your question.
Yeah, so actually that's exactly what I was asking. So normally when we define entanglement entropy, we know there is a thickness because it's not, there is no density matrix in the operator algebra, and we know how, and the cure comes since the fact that this divergence, after all, is completely independent of the state, and if you look at the field dependent part, it's kind of well defined. So in this particular case, there doesn't seem to be some kind of resolution of a similar kind. So I mean, one can probably try to phrase what you're doing better in terms of the modular theory or something like that, so that one understands it better, or if you misunderstood. So this.
Yeah, no, I would like to understand indeed some boundary theory understanding of have a boundary theory understanding of the yeah. So otherwise. But it's not clear for like for local field theory information, where I can run Wilson's argument to show that the local correlation functions, how they can possibly decouple if the in terms of the usual renormalization group.
Normally, we start from something that is RG invariant, right? Like when we talk of this modular theory, we get this modular operator is sort of an RG invariant quantity, and then of course you could, from that point of view, you could talk more about RG flow later, like in terms of like going to some subalgebra, like encoding some your long distance and a short distance algebra into a long distance algebra, and then defining the modular operator in that operator algebra. So in that way, you could have some notion of RG, yeah. But here, in your story, it doesn't seem there's an obvious modular theory to describe this.
No, you're right. There might be a way of so I have been looking at the literature on RG flow of entanglement entropy. So in 1+1 dimensional, conformal field theory, there is a nice, there are nice results due to that. One of them is due to Shromik, and but I couldn't apply them to this thing. But yeah, for correlation functions, there's Callan-Simanzik equation and so on and so forth. The standard ways of saying that okay, the decoupling of the high energy degrees of freedom are happening. So there is no such simple thing. At best, you can make an entanglement entropy, the Rayleigh entropies, into a partition function. Okay, in that language, it's not so easy to. But it's just that it's not happening in case of ADS 3 cross something onwards, ADS 3, ADS 4 cross something. How it's related to the appearance or not of a mass gap in the transverse direction. That also is an interesting stuff. So two things are happening together. One is that there is in ADS 3 onwards, there's a mass gap that's appearing in the transverse degrees of freedom, and also the UV physics is not decoupling. Maybe there is some relation between that. Right. All right.
More questions? Yeah, Neela, you can speak up a little louder.
Okay. So, Gautam, when you did this ADS2 cross R3 and patched it to ADS5, for example, in an extreme alarming case, then there is no limit on the subsystem size on the ADS5 boundary, right? I mean, what I'm trying to say is we know that if I compute the Ruita-Kanagi area,
Yeah.
the major contribution comes from the region where the Ruita-Kanagi surface bends.
Yeah, let me tell you what, because I went over it so fast. Yeah, so let us say, ADS4 going to ADS2 cross R2. So this is ADS4 in the Poincare coordinates. Okay.
Right.
So, so this is what it is. So you start with a near extremal Reisner-Nordstrom black hole in ADS4. So this is actually ADS4. And this is how it looks like. Okay, so there is a certain dilaton that appears, which in this case is just R. In case of the Reisner-Nordstrom black hole, but of course we do our analysis more generally. Okay, so this is actually R2. So this is non-compact. It's completely non-compact, and in that R2 we consider an infinite strip, which is finite in the y direction and infinite in the x direction. That's the strip that we consider. And we consider the Ruita-Kanagi surface starting out from that kind of a region and which goes and turns like this. The surface also has an infinite extent in the x direction, and you can compute the area of this. So this delta x is the extent in the x direction, which is actually infinity. So you can compute this rather easily, well, at least numerically. But in the IR region, the IR contribution, you can show this, that's for sure, that the full area is some IR well-defined, isolatable IR area plus some UV divergence. Okay, and you can just get rid of the UV divergence by some subtraction, and the area of the RT surface. So in other words, if you think of a sliding cutoff, that the cutoff is taken from here to here, this amount of the area, okay, you can identify with the IR field theory. And you can also show the dependence of that area with the sliding cutoff, and is given by this. So when you use the UV-IR correspondence between radius, the radial coordinate, and the sliding cutoff, then in terms of the sliding cutoff, the entanglement entropy is something which, the first term is something which is the IR limit. That is something that you expect in a conformal theory, that this is just like for temperature, you would have had n squared t square here, and times the two-dimensional volume of the theory. And that would be the IR limit. But then there is exactly like an RG flow equation, which is delta lambda by lambda. But okay, now I said it a little more clearly, but maybe this is not exactly what you had in mind.
What actually I was trying to understand was, if I compute this area, then the major contributions of that area comes from the region where the surface bends.
That is, well, yeah, meaning that there is an infinite contribution that comes from the horizontal part. Okay, so from the horizontal part, from this part, but you have to get rid of it.
Okay, yeah.
Yeah, so it is this one which you can isolate. Okay, and you can get rid of it. For example, what you can do is to take this area, RT surface, and compute the same RT surface in a non-black, in a pure ADS4 space-time. And you take this RT surface minus the RT surface in pure ADS4. Okay, that also does the job of subtracting away this horizontal part. What happens is that the this thing here, for the pure ADS, there is no black hole horizon here. It just goes a little bit more. Okay, and basically, if you subtract out if you subtract out the blue part and the red part up to this surface, then the red part just cancels out the blue part completely. So that's what happens. So up to this cutoff, sliding cutoff, it doesn't really matter whether this horizontal part is coming from a black hole geometry or from a pure ADS geometry.
Yeah.
So you can just subtract out.
Okay, thank you.
Okay, any further question? I have to actually wind up in 2 minutes.
Thanks a lot. Thanks a lot, Oyon, and thanks a lot, all of you guys. And so I hope you get well soon. I'm so worried that you have the dengue here.
Yeah, I hope so too. Very soon. I mean, I'm recovering for sure. So it's in the positive side. So
All the best to you. Okay,
Yeah.
great.
Okay, any question more? If not, then we can. Lata, you have any question or is fine?
I don't have any question. I didn't know about this target space entanglement entropy, and I'm very curious to understand what it can tell us in a many-body quantum system. For example, where can we use it? Or
Yeah,
I'm
discuss
tending to
this,
think
Lata.
towards, like, if I have a qubit, and can I tracing out more degrees of freedom, just learn about qubit, or often in maybe this should be not recorded.
No, this is a new tool, and it should be used. I think like in diagnosing phases and so on and so forth. The entanglement entropy plays a lot of role.
Yeah.
So why not this one? So
yeah, exactly.
So
Interesting. Okay, so good. So let's thank Gautam again, and see you then next week. And have a nice evening, all of you. Bye.
thank you.
Bye.
Bye.